Professor of Biophysics in the Department of Membrane Research and Biophysics at the Weizmann Insitute of Science in Israel. Since 1971, his research has focused on various aspects of membrane structure and dynamics. Currently, his main interest is manipulation of membrane fluidity for clinical diagnosis and treatment. He's published extensively and is acknowledged worldwide as one of the leading experts in the increasingly significant field of biomembrane research. His patents range from anti-tumor vaccines through the use of schizophrenia-linked peptides to a positive use of CO2 to trap insects. He's utterly fascinating, and it's probably the best way to describe him. And here's Professor Shinitzky.
Just to help you out in my presentation, I have here hard copies of whatever you will see here. So whoever wants it, just end up your fingers, and I have 20 of them. Otherwise, you simply can follow what is written in there. It's simply to make it easy for you to put.
Okay, Professor, come up here and let it go.
Yes.
And I'm going to give you a 10-minute warning, and you can run into your questions.
No,
okay. Okay. So
here we are in the Festival of Symmetry, and I'm going to talk about symmetry, nothing else. We just... Yes. It is very interesting that when we talk about symmetry, as we heard this yesterday, people focus mostly on the standard model and the way symmetry, with all of its complications, is introduced. I'm going to talk to you about one level higher, which are simply molecules. Asymmetrical molecules, which are called chirality, and we have a whole session on it. But I would like to expand it to the whole universe, from molecule to the universe, and it may sound kind of bold and extreme, and just to make it even more so, I would like to start with my last slide. So the first slide and the last slide are the same, and just want to show you what are the conclusions that I'm trying to get into. So, sorry, here. I call it assertions. They are still tentative, and this goes as follows. The first, so to speak, assertion or assumption is that our universe is actually a 4D array, and of course we know space, time, and so the combination of it. So it's not new, but it has three-dimensional asymmetric spaces which are secluded by a fourth dimension. We'll talk about this, and don't worry too much about it at the moment. Now, we must consider in all of our talks, and in all of our presentations, in all of our mathematics, that our mind, which was sorted out by evolution, can just face three-dimensional type aspects. All the rest comes later on in mathematics, but despite this fact, nature, in my belief, is actually a fourth-dimensional type array. What can we do that evolution forced us to stay in the three-dimensional case, and this is what we are going to do. So if you're taking the first assertion, if you move further, so you have, when you translate the fourth dimension into the three dimension that we live in, which are called the realm of our life, you end up with a situation that our universe, our space around us, and everything else has kind of a preference to one side versus the other side. And this is what he calls the asymmetrical space. Now, if this is the case, then there is a definite, absolute definition to right versus left, which is a very hard thing to accept logically. and clockwise and versus anti-clockwise. Now, when we take the first assumption and we combine it with the fourth well-known space-time fourth dimension, then we end up with the fact that this fourth dimension of space and time, maybe they are interrelated, or maybe they're the same. The fourth dimension, which creates the separate spaces, maybe this is what we term as time, emotionally, whatever. Again, don't forget that when you approach such a case and ask ourselves, what is time? We cannot evaluate it because it's a fourth dimension, and our mind is not constructed to accept it, but rather to evaluate it, I would say, in kind of a sensitive way. Now, let me start from the step by step now. When we talk about molecules, we have a very strong kind of experimental tool in our hands. If you talk about asymmetrical molecules, and you ask yourself, what happens if I place them together in one vessel, in one tool, in one aggregate, and so? There are a few such examples which appear in nature, and these are liquids which are made of chiral molecules. There are not many. Actually, all of them are listed here in this list here. So, in other words, you have randomly oriented molecules in a dish or so, and then you say, well, is the right-handed dish versus the left-handed dish are exactly identical? And if you just take from the literature, values from the literature, it works. No.
No, it won't work. Just press. I got one for you.
Oh, it works. It works. Yeah.
Sure?
Okay. Yes, it does.
Okay.
You see, you ask yourself, well, let's take a very cool dimension of the density. If you measure the density of a right-handed versus left-handed, this is called R and S, and you ask what is the ratio of these values, and this is from the literature, this is not our work. You see it is very, very close to 1, but it should be precisely 1, but it's not at all the case. You can say, well, it's an experimental error and so on. However, there is by far more sensitive value, which is called the optical rotation value, and we'll mention it later on. This has a kind of an autocatalytic, or if you wish, autocatalytic type effect, that one molecule affects the other, and then the ratio, look what different values. The ratio should be 1, but it's not at all the case. In particular, if you take limonene, and you take it from one reference, the other reference, and the Aldrich supplier, and you find values which are about 20 or 30% away from one another. This is totally unacceptable. If you take another example of assembly of chiral molecules, this is a display of secondary butanol, 2-butanol. This is one of the simplest fluid, which is chiral. And you make a saturated solution in water, precisely the same concentration, and see what happens. Simply with your eye, you can tell it. You see, this is the R component, and this is the S component, and you see they look to the eye, they are different. We have some papers on it, and the energy of it, and so on. But just qualitatively speaking, you see they are not at all similar. I'll give you a few more examples. This is actually my first paper in the area 20 years ago when I entered in, and you do the following. You take a chiral molecule, which is serine, the amino acid serine. You attach to it a long fatty acid, which is stearic acid, which is a very simple chemical reaction, and you end up with N-serine, L-serine, and V-serine. Well, if such a molecule is placed in water, it is well known, it will form micelles. Again, aggregation or in an area where the domain of attached molecules is created. And then you say, well, I'm going to measure the optical properties of it. This is what you get. This is the circular dichroism. It's a very simple method of the L. So the shaded area is the ranges of many experiments that we have carried out. And this is what you have, it happens with Z. It's the opposite. This should be the case. And it's very convincing because when you add alcohol to the system, and not too much, the liposomes fall apart, and I mean the micelles fall apart, and you end up with a totally different spectrum, which is here, which is identical to here. So in their aggregate, they are totally different by about 50%. So again, something which we must consider, and this is another example, again from 5 years ago and so, we prepared a poly-L and poly-D glutamic acid of the same length, each of 24 amino acids, exactly. Now, such a polymer, also well known, has a helix coil transition and so on. Now, first of all, if you measure the properties of these two polymers, they are not at all the same. You see, if you just do the water part, and we heard about this is my contribution to the water section. So here we have it in water which is very different, and there are many aspects that are different here. And when you do it in D2O, they become a bit closer, but not exactly the same. So again, poly-L and poly-D, from the cooperativity point of view, and so they are not the same, and whatever you want. Here comes a very interesting experiment that was published a few years ago, and I can ask the chemists here in the audience if they would accept it. Assume that you have a solution of an amino acid in water. Let's say 1 molar, whatever, alanine or water in water. You have the D and the L. Now, you take the L and you mix with the L with the same. You mix two identical solutions. Of course, you wouldn't see anything because you just mix them together. However, when you mix L with the D, energy is liberated, and it's energy due to entropy. But I won't go into this. So this is, I would say, as we say, it's kosher. It may be accepted because you release the entropy, the T delta S is being released, and so on. But see what happens here. When you add, this is by microcalorimetry measurement. By the way, the energy is very, very low. It's calories, but it's there. It's only calories per mole, not kilocalories, which is the common energy level of a chemical reaction. It's calories per mole. So if you add a D to L or L to D, there are two separate features of the system. Again, telling us that something is here is strange. Now, so this is kind of screening of what is known in the literature. How has this been explained? And this is very important. Not by us, by other people. How people would explain why there is a discrimination in nature all around for one type of chirality versus the other. First of all, people have noticed that people have calculated that the parity violation in the weak nuclear force, which is very well documented and so on, can introduce, you see, the parity violation actually induces a field which on its own is chiral. It has a certain chirality. Now, when chirality meets chirality, or like meets like, if you wish, then something happens in energy. So if a right-handed will meet right-handed, or a right-handed will meet left-handed, you'll see two different reactions. And people have calculated it, and they say, well, like in amino acid, the parity violation will react with the asymmetrical electron cloud. What will be the net? And they figured that L amino acids have a lower energy than D, but the difference is minute. It's very, very, very small. It's something incredibly small. So it's completely irrelevant, if you wish. However, then people say, such a tiny, tiny difference, and we know it in nature, can be amplified by autocatalytic or cooperative processes. And examples for it is when a crystal grows. And we have shown, in one single case I admit, but it's enough, that if you take saturated solution of tyrosine, it so happens tyrosine, and you let crystal grow, you see that the D goes much faster than the L. Again, something totally unexpected. So in the crystal growth and in helical turning, this is what we saw with the polyglutamic acid, helical condition, and so on. There are many such examples. Now, one word about water, what we just heard such a beautiful lecture before. Now, water also enters into the game. When you go back to the parity violation and its field which creates this asymmetry between L and the D, beyond this thing, there is one thing more, which is a creation of a magnetic field, a tiny, tiny magnetic field in only one element. The L amino acid have a tiny magnetic field versus the D. And this has been shown by others years ago. Then, let's go to the water. Water, it hasn't been mentioned, I must say it here. Water has two separated isomers, the molecule. One with spins which are parallel, the proton spin, which is called auto water, and the other one is the power water. And this has been known from the beginning of the 20th century. However, a Russian group like 10 years ago have demonstrated that the auto water and power water don't talk to each other. Actually, in the glass of water, we have 75%, and this is due to the properties, and to talk about it, 75% of water is auto water, and 25% of water is power water. Fine. However, the auto water has a distinct magnetic moment. And if L has also a tiny magnetic moment, then auto water will love more to stay around the L, while the power water has no preference. So this may explain why do we see a difference between reactions in H2O versus D2O. And this is one of the most important information that we have. So altogether, this is how people have accepted it, why there is a chiral discrimination in nature, and the build-up in biology, and so on. Now, last year, I mean, maybe this year, I published a work that said, well, all what I showed you before, it's hard to accept on these principles that I showed you. And it could have a very, very simple explanation. That in the creation of our universe, what we call the Big Bang, there was an accidental failure in keeping symmetry. And this is known in the nuclear standard model. However, this could be extended by far faster, and saying that the symmetry has been also kind of diverted in the space itself. The space itself is asymmetrical. Well, so this is a big statement. If you wish, I have a full paper on it with all the arguments here. If anyone wants it, I have it in hard copies and so on. So, what then does this mean? So, here it is that you was associated with accidental breaking of space symmetry which is implicated in the standard model of atomic nucleus. This discrimination between isomers of chiral molecules, namely some kind of preference for one type versus the other. You remember, I showed you data on that, but I showed you the conventional explanation, but I believe it is by far too, I mean, we cannot explain exactly what we see. Now, the homochirality of living system, the chiral imbalance, if you wish, I can talk about it, about some spiral galaxies. And if you wish, we can go further and say without this, all what we know about thermodynamics wouldn't exist. All what we know about flow, temperature, and so on will never exist if everything will become symmetrical. And philosophically, you could go even further. They say, well, assume that God, whoever created the Big Bang, we have occasional Big Bangs. The way to is by taking as a model of what they call equivalent sphere. And I'll present you this model in just words. You say the following. Assume that I have a sphere which I claim is asymmetrical. How can you see what is asymmetrical, in what way? You say, well, let's take an equivalence case which operates, and I'll show you the practical part of it is very interesting because this has been used years ago by many people without knowing what they're doing. Now, in our practical way, we say, well, we have 3 dimensions in Euclidean coordinates. Let's take the z is the dimension of perpendicular to the ground. So this is completely symmetrical. The y direction is back and forth, symmetrical. Then you create a plate, and this plate is symmetrical and everything is fine, classical. Then, perpendicular to this plate, you have the x-axis, so it can go right and left. Then you say, here the asymmetrical, here comes the asymmetry. The asymmetry is between right and left. If you accept this model, then there is a definition, an absolute definition for right versus left. We call right left according to our convention. We say left is where the heart is, and right and so on, but this is passed from father to son, saying you describe it, but it has no physical meaning. And actually, physicists have long, philosophers have worked out all kinds of ways, without any success, how to transmit the direction of right versus left to an alien who is super intelligent and different. The only way today that people would accept it is by using the Lee and Young experiment of the parity violation and telling to construct it there, and then to the parity violation to say which direction is right and which direction is left. So when we construct it, we define right versus left, and if you feel in the polar coordinates, which is exactly the same, you define clockwise versus anti-clockwise. But it's interesting that exactly this approach people have used. I mean, Pasteur was the one who used it. And he asked himself the following. Assume that you have a solution of a chiral molecule in, let's say, in water. It's kind of a random distribution of a chiral molecule. Now, the whole system as such is an asymmetrical system. The whole space that is created is asymmetrical. How can I define it? They say, well, let's take what I call now equivalent sphere and talk about one dimension. What was the dimension that has been used? Is the polar, is the direction of polarization of polarized light. If you need to rotate it to the right or to the left in order to compensate for the right and left sensitivity of the system. In practice, what you do, I don't know if you're familiar with it, you shine polarized light, you have the system in between, then you have another polarizer which darkens the field. However, when you have this system in between, you need to shift it a little bit, and then you call it right or left. And up until now, this is the way you define chiral molecules, the way you rotate polarized light. So this is actually a very old approach to the system. Now, let's go now back to the proposed asymmetrical space. Now, we said that at the fourth dimension, we have three-dimensional spaces which are separated from each other on the fourth dimension. Now, we need this separation because otherwise there is a kind of reaction which is called racemization. They kill each other. The spaces which are of opposite direction, they just merge together and there is no any more preference to any one of them. So if they are separated, and what is the weight, and if there is two or more of them, this is described here in two components. One which rotates. I mean, this is the way to, but it's of course simply a pictorial way of presenting it. Now, what do we have in this space asymmetry? So you have a 4D array which accommodates space entities of opposite symmetry, and I don't know how many, it doesn't matter too much. Now, when we translate it, and this is our mind that does it, it's not a reality, our mind takes the fourth dimension and says, well, let's present it in a three-dimensional case because this is all what we can do. We know now that the fourth dimension, this has been described long ago by the general relativity, and so that it is the time. But at the same time, I say that this fourth dimension is the one that separates these entities which create the space asymmetry when they merge together in our universe. Now, if this is the case, then I come up with a very kind of a bold statement that the time dimension and the dimension of space asymmetry are actually interrelated, analogous, or the same. It could be the case. However, here there is one, I would call it a trap, experimental trap. When such a claim is made, there is a way, operational way, to verify it experimentally. Here you cannot run away. You can say, well, you claimed it, and let's do it. And I would like to show you, to show two experiments. With this, I'll finish. The first experiment is rather, I would say, it's rather interesting. And this is the following. There are a list of just a few molecules that happen to be completely non-chiral and completely symmetrical. That for some reason, the reason of course is the molecular forces, they create chiral crystals. The most famous one is of course silica. Silica is silicon dioxide, and it forms Z or L crystals. And just to describe it to you in a very simple sense, assume that these are the molecules, that they are identical molecules, but when they meet each other, they form a dimer like this. Now, a dimer like this will start to create a crystal which has a chirality, clockwise chirality. However, if they will form the dimer like this, it will be a left-handed one. So it's all statistical. So one of these molecules, there is a very short list of it. I am familiar with 6 or so such molecules. The most easy one to deal with is sodium chlorate. Sodium chlorate. which I don't know, students they do experiments with sodium chloride, which is a very interesting case because a saturated solution of sodium chloride will create spontaneous crystals, and statistically about 50% will form the D and the 50% L crystals, and you can collect them, do whatever you like. The idea was then to use single crystals of sodium chloride, just as such, separate out the D and the L, and then create an X-ray analysis of each of them. If I'm right, the volume or the dimension won't be exactly the same. By how much different? Just extrapolating from what I showed you in the fluid, chiral fluid, by estimates it's between 0.1% to maximum of 1%. This is the range, but it's still physically important. This is the case. So I must admit that the experiment is quite difficult. And I'm going to show you this is being exposed for the first time to the audience, our results with 5 separate crystals of sodium chloride. And I admit though, so this is X-ray analysis. It's of 3. These are 3 sodium chlorides which happen to be D. This is uncontrollable, you know. You just collect them and you pick up the D crystal and you put it in the X-ray diffractometer. And these are the L. As it seems now, you can say statistically it's not yet completely done and so on, but still it hints about the trend. And if you take the density of these crystals, the difference is about 0.3%, which falls in exactly the range that I was talking about. Of course, more work has to be done here, but this claim that I made before can be truly measured, and there is no way to, as I said, to escape this problem. The next one, which is by far more important, but by far more difficult, is time and space are interrelated here because of the of asymmetry. So this is the last experiment I'm going to show you, and this was as follows. Now, you expect to see a time difference between 0.1 to 1% in an environment which in 2 environments, either right-handed or left-handed. Now, to measure time in 0.1% difference is not at all easy. And there are very few systems that you can select. Like we have tried, for example, kinetics of first-order kinetics. I'll give an example. First-order kinetics of racemization of amino acids. This was their first idea, but the statistical deviation of the results wouldn't allow us to come to any conclusion. We have carried out in our atomic reactor in Israel the following experiment. We have selected a radioisotope, gallium-67, which has a short lifetime of 3.26 days. So here you have a case that you can measure. You put this gallium in an asymmetric field, and we have selected the 2-butanol. Gallium itself can be dissolved in 2-butanol. And so the results are shown here. They're not very impressive, but this is after a lot of work. And this shows you what are the measured half-life of gallium-67. This is the literature type value, and you see they're all spread around quite well around this literature value. The S is here, the R is here, but if you wish, there is kind of a trend in this area, and I wish I would like it to be statistically significant, but the statistic here is not as good as I thought, but at least the trend, you can see it, you can feel it, and of course, worthwhile continuation. So this is where we are in this respect. And that's, again, I'm coming back to the first and the last slide of my talk, which is here. And now it's more clear to you. So the brain is made of a 4D array. And you have always to consider the fact that we are using our brain, which cannot accept it, even not emotionally, what happens in the 4th dimension, and our jokes about it, but I'll tell you. So if you say that in the 4th dimension there are these universes which are asymmetrical, and they merge together in our 3-dimensional array. They merge together in our brain, not physically. They are there to begin with. And then you create right versus left, and clockwise versus anti-clockwise, which are defined in their direction, and we can explain all what I showed you before. And this 4th dimension of asymmetry may coincide with what we call time. It will give us explanation. We sense time, we know what time is, but of course, in practical way, of course. But what is it actually? Where does it come from? Who created it? And it could be very well be that the explanation that I gave you here that will cover it. Thank you very much.
Professor, can you take some questions now?
Yeah.
Over on the right.
You directed.
Go ahead.
So, if you are predicting that our universe is a result of 2 opposing 3D spaces that are merging, what signature would you predict we should see in the cosmic microwave background?
Yes, this is all kind of a simulation. It's just a presentation for our eyes and our brain. How does it operate in essence? I don't know. There is nothing. But one is exactly the opposite of the other. In what way? No. You come back to our mind. How do we accept it? There was this joke about the guy, the guy with his teacher. And the teacher showed him a piece of paper. And he said, well, now assume that we are 2-dimensional creatures. And we are here, we are stuck into this. Now, this is a prison. And you need to run away. How would you do this? And the guy looked around and said, oh, it's impossible, we are 2-dimensional. So he asked his teacher, how do we do this? The teacher plugged his finger and said, to the 3rd dimension. So this is something which we cannot accept so easily.
I am referring to the slide of the titration of L and right proline.
Yes.
And the fact that you say that you have only something of a calorie per mole difference of energy mixing.
Yes.
And I think this calorie mole translated at the atomic level is of the order of 0.1 milli-electron volt per molecule. And the 0.1 milli-electron volt, I wonder if this is correlated with the difference of the orientation of the magnetic moments of the ortho and para. And in this case, time would enter because the magnetic moment conveys within it, in its definition, a spin, and a spin is a current rotating in time. So I think
no, but we may be right. The interpretation is not so simple here. But what I wanted to show that there is a difference when your L goes into the V or D goes into the L, because you would expect it to be exactly the same, but they are not. You see, this is the point that attracted me the third.
The difference of the order of 0.1 milli-electron per molecule, and this could be associated with the interaction of the magnetic moment, which are also defined in time.
Yes. Right.
Any other questions? Yes, Larry?
3 brief questions.
Speak up, Larry.
3 brief questions. One is how to measure, make fine discriminations between the difference of right and left via the pitch. So there's something called the Frenet-Serre formulas, and you can determine from the geometry what the pitch is of the 2 molecules, the right and left. And I'm wondering whether there's a difference there. So the second question is that David Attenborough has a way of actually measuring the degree of symmetry that you mentioned.
Yes.
And whether you use that at all, whether you think it's useful. And the third is, time is a measure of symmetry. In relativity, of course, you have different measures of time depending on your inertial frame of reference. Is that relevant, or do you care just about in one frame?
You see, all what I presented to you is classical, conventional, without going into any relativity type aspect, because this has to be broadened with it. I don't want to touch upon this, but it's enough in the classical way that we already see some deviations.
What about the other two questions? You would not. Okay.
Yes, sir.
If you're going to see chiral asymmetry on a scale that you're talking about with these molecules and their volumes and so forth, it seems to me the place to go is to the highest precision tests we have. And at least my quick thought, the highest precision tests we have of the chiral symmetry of the universe are G-2 measurement of the electron, which is out to something like a part in a trillion, and also looking at the properties of the photon. If you have a chiral asymmetry, you would see birefringence, I believe, in the propagation of light in the universe. And those two things are incredibly strongly constrained, and I doubt that you could get a 0.3% differentiation in volume there without seeing an effect in things which are measured down in parts per trillion or better. I don't know if you've thought about those things or not.
Yeah, but you're right, but whatever you claim, you must always say why you see it in one system and not in the other. What is the discrepancy? And this is reproducible. It's not something that comes up so you have always to find that. Some people tell me, well, there is radiation, circular polarized radiation, circular polarized radiation. What created it? Why circular polarized radiation to one side and not to the other? So always this imbalance that attracts we need to face. Why is it imbalance?
Yes, sir.
You mentioned that silicon dioxide forms chiral crystals, so that means we have left and right oriented quartz. Do you have any information whether the quartz appears in exactly the same proportion in nature, or whether one or the other is preferred?
It's something that you can make just a guess and whatever. I'll give you some indirect answer. I was arguing with people that if we create in nature, let's say in biology, bodies, assume that you put a mirror and you face yourself in the mirror. So now assume that I create such a body physically. I have a body which is based on D amino acids, and all the rest are the opposite way. Will it be identical in all aspects? And what I'm claiming here is not. These two bodies won't be identical. So say, well, how do you prove it experimentally? And there is one finding in the literature that was kept silent. And there is a group in Chicago that have synthesized a very simple enzyme which is just made of D amino acids. And they show this, the reflection, everything, all the measures are the same. However, the reactivity of this, the D amino acid enzyme was about 10% less than the L one. And there was no explanation. According to this hypothesis, there is a preference to one side versus the other to begin with, a priori. Yes, that's all what I can say.
Yes, sir?
I refer to your first point right now, the tentative one. At CERN in Geneva, they have a huge research project to investigate experimentally, but in high space, whether there is another universe consisting of antimatter. And the question is, the boundary, of course, they would annihilate each other. Now my question, your two three-dimensional asymmetric spaces secluded, could this have any relation to what they do in CERN?
In what?
In CERN, the Large Hadron Collider. They have a second research project worldwide of finding a universe of our universe and an antimatter universe, separated in your language by a fourth dimension. Is this the correct conclusion?
Again, I can just tell what I expect. Everything that you talk about antimatter is a mirror reflection. It's symmetrical. So everything that we spoke here about matter can be considered the reflection, of course, to the antimatter. That's all we can see at the moment. Again, there I would expect to find asymmetry, even in the antimatter world. Otherwise, you see, if things are symmetrical, you would never be explained what is thermodynamics, why things move, what is entropy. There is no explanation to it in a simple symmetrical world. Yes, in a symmetrical world, nothing will move. A second law of thermodynamics, which says it's a one-direction movement, will never exist because of annihilation. One process will annihilate the other. But we can talk about it.
Yes, sir.
In trying to relate your presentation to my presentation, you know, many of these chiral molecules have ordered water next to them, for example, a sodium chloride crystal. And I was just wondering, this easy water I was talking about, you can have any of 6 different orientations. You can have 0 degrees and 180 degrees. And I'm just wondering whether it's possible that in some of the molecules, let's say a D would have 0 degrees and the L would have 180 degrees.
That's a good idea, yes. But you have the tools to figure it.
Yes, we do.
But you never spoke, I wonder, about the auto-water versus and you know, I bet you that in the extruded zone, it's mostly the auto water which is extruded. And this is easy to measure because it's become magnetic. It will have a magnetic impact.
We should do that.
You know, that was a great question to tie both the keynote and plenary speakers together. And I really want to thank both of you guys for doing a great job. Okay, we have a break now, folks.